Okay, we are looking at lab 10, which is the Opamp imperfections lab, and in particular we're looking at part 3, which is the most fun part of this lab. It's kind of the clincher at the end, and this is the only part that I really think is worth doing in the real hardware if you want to be selective about what you do in the real hardware. So a high gain AC amplifier. Yeah, and in particular in part 3.2, which is the part we're really building here, 3.1 doesn't really have anything to build, we're going to connect a microphone, and so then we're going to amplify a microphone signal, which is a pretty small signal. We're going to amplify that with a big gain, like a gain of 100, and we're going to do it in a way that the DC gain is just 1, but the AC gain for audio signals is like 100. And that's sort of a convenient thing to do because all of the op-amp imperfections like I bias and V offset and so on are DC phenomena. Okay, so they're all like constant as a function of time, whereas an audio signal is, there's no DC component. It's all time varying. So this is actually a really good trick. If you want to amplify a signal which is entirely time varying, the DC part doesn't matter, then we could just sweep all of these op-amp imperfections, the DC parts, under the rug. So we're going to build ourselves an amplifier that has good gain for signal frequencies. In other words, audio frequencies are kind of tens of hertz up to a few kilohertz, let's say. I mean, actually, an old-fashioned telephone goes from about 300 to about 3,300 hertz. But I guess in principle, audio goes from like 20 hertz to 20 kilohertz, but you don't really need the super high end. Anyway, so we're aiming for signals that are kind of the few kilohertz range. So this looks really complicated, but let's first boil it down to its essence. So first of all, now this is a non-inverting amplifier. It's not an inverting amplifier. So here's the input signal, and it's coming into the non-inverting input. And then here we can do the kind of standard thing here with, we'll call this R2, and we'll call this R1. Okay, and here's the output. So then we have the usual result is V out over V in is 1 plus R1 over R2. Okay, so if R1 is 100 times as big as R2, then the gain is 101. And I think we had an earlier circuit where R1 was 1,000 times bigger than R2, so the gain was 1,001. Typically it's like some round number plus 1 because you make this ratio some round number. Okay, so that's the basic form of it. And, oh, by the way, the way you derive this is actually kind of cool. You say, oh, I take V out, and I use the voltage divider equation. So this is, you say what appears here. The voltage that appears here is V out times R2 over R1 plus R2. I can't help digressing, sorry. So V out equals this thing. I'm going to call, right? I'm going to just, by the way, this thing, op-amp feedback requires this to be the same as V in. So I'm just going to call this V in. V out, oh, wait, I wrote it backwards. V in is V out, right. So you say what appears here? What appears here is going to be made equal to V in by feedback. So V in equals V out times the voltage divider result. So there's R2 over R1 plus R2. So now you solve for V out, and you get V out equals V in times R1 plus R2 over R2, which is the same thing as V in is V out 1 plus R1 over R2, right? So that's the same as this result. Okay, I couldn't resist. But okay, so that's the basic version of this circuit. Now, suppose that I am able to make R2 go to infinity for a DC signal. And the way I do that is, okay, I stick a really big capacitor here. And I want to make the capacitor big enough that at my frequency of interest, like my audio frequency, the frequency is so high that the capacitor just appears to be a short circuit. So it's as if the capacitor were a wire. But then you know that at zero frequency, at DC, the capacitor will look like an open circuit. So it's as if it's an infinite impedance. If you make R2 be infinity, then the gain is just 1. So we want a big enough capacitance that the impedance is tiny at signal frequencies, so it doesn't interfere with the signal frequency. But we want the capacitor to be present so that at DC, where the impedance of the capacitor is infinite, that basically makes this denominator here be infinity, so V out over V is just 1 for DC. So that means if we have some effect due to the bias current in the op-amp, some effect due to the offset voltage in the op-amp, it only gets multiplied by 1, which isn't too big, whereas for the audio signal that we want to amplify, we have a nice big gain of 100. So that's what this is for. And then I think, by the way, I asked you to do kind of just the really basic math just to see what's happening with the impedance of this capacitor. Let's just do that really quickly to speed you up. Yeah, so if we pick some convenient signal frequency, so 1.6 kilohertz is kind of right in the middle of the audio range we're interested in. You say, how big is the impedance of this capacitor? Well, it's 1 over j omega c. How big is the magnitude? 1 over omega c, so omega is 2 pi f, so 2 pi is like 6, and then 1.6 kilohertz, that's like 10 kilohertz, 10 to the 4, that's like 10 microfards, 10 to the minus 5. So you put it together, you get 10 ohms. So 10 ohms is quite small compared to this 100 ohms. So you can see that by the time you're at 1.6 kilohertz, the presence of this capacitor basically doesn't make any difference. So and that's what we want. We want that at the audio frequencies of interest, the presence of this capacitor as if it were just a wire. So that's pretty good. Okay, so that explains everything here. We have our 101 gain amplifier at signal frequencies. It's just a times 1 gain amplifier at DC. We have our power connections. Then you say, okay, what is this stuff on the left? So we have the microphone. Now this microphone, actually, it wants to be powered. It has there's a little field effect transistor inside it that it gives a little bit of amplification. So it wants to be pulled up to like 5 volts. So it wants to kind of sit near 5 volts, but it's not exactly at 5 volts. Because if it were exactly at 5 volts, if you connected this directly to 5 volts with no resistor, then this point would just sit exactly at 5 volts and you would get no time varying signal. So we connect it to 5 volts through this resistor, and then the current varies a little bit, which causes this voltage to be a little smaller than 5 volts. So normally, if you look, when we look later with the scope probe, we'll see that this point stays pretty close to 5 volts, just a little bit less, but it kind of wiggles up and down. So then you do get a signal, okay? So the fact that it kind of sits near 5 volts is what it needs to be powered internally. And then the fact that it wiggles around gives us a signal that we can look at and amplify. But we don't want the input to our op-amp circuit to be near 5 volts. We want it to be near ground. So we use this capacitor. This capacitor just blocks the DC signal. Okay, so then again, the 5 volt, or the approximately 5 volts, stays to the left, but the time varying part gets through to the right. So that's all fine. But if we had that, if we didn't have this resistor, then the bias current, there is a small bias current. It's like tens of nanoamps for the 741. It's like about 100 nanoamps. And it flows into the 741 input. And if there were no DC path to ground here, or if there were no DC path to a fixed voltage, then that current would just charge up and up and up and up and up this capacitor, and eventually this input would be big enough that the output would saturate. And I think we can see that. We'll try that in a minute. So we need some kind of a resistor here to prevent the the bias current from charging up this capacitor. You say, how big a resistor do you need? Well, if you made it like a gigaohm, then the bias current times this resistance, I bias times this resistance, would then be big enough to create a significant voltage. So you don't want it to be absolutely ginormous, because then I bias times this resistance would be big enough to saturate the output at the plus or minus power supply voltage. But if it's too small, then you have an RC time constant here that's too small. So you want it to be big enough that this capacitor looks completely, this is basically a high-pass filter. You want the high-pass filter to have the longest possible time constant so that it passes even very low frequencies. But you don't want the resistor, there's often a trade-off in electronics, but you don't want the resistor to be so big that the bias current flowing across this resistor gives you a significant voltage here. So omega ohm's a pretty good value. Okay. Okay, so we built this circuit over here, and so we'll look more closely at that in a moment, but let's kind of go around the circuit diagram a little bit. And so for one thing, we put the op-amp symbol kind of upside down from the way we normally draw it, because the input is into the non-inverting input. The feedback is always through the inverting input, but we put the non-inverting input up top in this case. So here's pin 3, so the input is coming in through pin 3, the non-inverting input. And then we're going to look to the left, and we'll see this 1 mega ohm resistor, we'll see this 100 nanofarad capacitor, and then farther to the left we'll see the microphone. And then we always expect to see feedback of some sort from pin 6 back to pin 2. So from the output back to the inverting input. In this case, that is through a 10K resistor. And then from pin 2, we will also have a 100 ohm resistor. And then instead of going straight to ground, it's going to go to this 10 microfarad capacitor. The 10 microfarad capacitor, you'll see when we look over here, it's this really huge capacitor. Okay, and then that comes down to ground. And then we've got, as always, pin 7 is going up to our positive power supply. Pin 4 is going down to our negative power supply. We're going to have a scope probe looking at the output on pin 6. And we're going to have a scope probe looking at what the microphone sees. And I think we actually don't have a scope probe here on pin 3 because I don't want to spoil the effect of this resistor. So I think we just have 2 scope probes, one looking at pin 6, the output of the op-amp, and one looking over here at the top of the microphone. Okay, so we can go look at that now. Okay, so we're looking at the circuit over here, and so if we go around the op-amp, pin 1 is a no connect, and then pin 2 is our inverting input, so the feedback should be there. So indeed you see this 10K resistor coming back from pin 6, the output, back to pin 2, the inverting input. And then we should see this 100 ohm resistor. So here's the 100 ohm resistor going over to one end of the capacitor, this gigantic blue capacitor here. The other end of the capacitor goes to ground. So it is my habit to use the blue power bus on the bottom for ground, and then I use the red power bus beneath that for minus 9 volts, or whatever my largest negative power, my negative power voltage. And then I use the red power bus up here on the top for my positive power supply, which in the case of the EE board is plus 9 volts. Okay, so we got to, so pin 2 was the inverting input, and then we have pin 3 is the non-inverting input, and that should go, so we have the 1 mega ohm resistor to ground, and we have the 100 nanofarad, so let's see where we go from there. So you see here's pin 3, and remember I can try to build the circuit so it looks like the schematic. So this little blue jumper wire brings us over to this point from which we have the 1 mega ohm resistor, that's this guy, goes down to ground. I guess it's hard to see that it plugs into ground, but it does. It plugs into this ground row here. And then we have this small blue 100 nanofarad capacitor. So it's going from that same column over to here. And then I wanted things to be kind of easy to see, so I put the microphone off to the left a little bit. So I have this green jumper wire going off to the top of the microphone. Yeah, so that's the only thing right, so the only thing that plugs in to the left of this capacitor is that little jumper wire going over to the microphone. So then from that little jumper wire at the microphone, we have from the bottom side of the microphone there's a wire going down to ground, but then somewhere here we have the 1K. Okay, so I was a little sneaky here. This is one place where I violated my rule where things should look like the schematic, because it was just too convenient to bring this 1K resistor down here to VCC. I didn't really know where I would put VCC if I put it up higher. I mean, so somehow it would be natural to have VCC like somewhere up here, so it kind of looks like the schematic, but there's only one thing that goes to VCC. So I said, okay, I'll just run this 1K resistor from the left side of the capacitor down to VCC here. But I really do try to make the built circuit kind of resemble the schematic so that I can look at it and see easily what's going on. And then you can really see the price I pay for kind of bending that rule here, because I couldn't, when I first looked at the circuit, remember where the 1K resistor was. Okay, so then actually I have there's this feature that I've never tried until just yesterday called the spectrogram mode. And actually, if you teach a computer to do speech recognition, which is something I always wanted to do when I was in college, but computers weren't very good back then, so I never quite got around to it. Actually, a spectrogram is the input that you provide to your machine learning algorithm, or your artificial neural net, or your Bayesian recognition algorithm, or your hidden Markov model, whatever it is. A spectrogram. So it's like for every time bin, you can see that I'm not really zooming in on this, but you can see that when you look at this, so in the top right here of the screen, you basically see time going from left to right, but time is kind of quantized. And then in each time bin, then on the vertical axis you have frequency, and it's going from 0 up to 4 kilohertz in this case, which is actually exactly the range you want to look at for identifying human speech. And then there's a color map, so the intensity within that intensity, or kind of the magnitude of the amplitude within that frequency and time bin, is shown in color. So you can kind of see things light up. So you can see as I'm talking, you can see that the pattern will change depending on the pattern of vowels and consonants. And then you don't really want to hear me hum, but I go, oh, 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 oh. I can really embarrass myself making a higher pitch sound. Ooh, oh, that sounds terrible. Ooh, that sounds really bad, so I don't know if I want to do too much of that. But see, there's a higher frequency, lower frequency. Ooh, ooh, ooh. Oh, okay. Then, okay, so we can avoid hearing too much of my voice. I've got a doorbell here, an old-fashioned magnetic doorbell. And watch this. It's going to go ding-dong, 2 different pitches. Oops. Let's see. Yeah. That's cool. You can see the first note is higher than the second note. You can see that. So that's kind of cool. Okay, back to the circuit. Sometimes it's just too much fun. Okay, so let's, I think we've done all of the, oh, and we can also look at where the scope probes are going. So we have, so we don't need the waveform generator in this case. Scope channel 1 is looking at the output of the op-amp, that's pin 6. Scope channel 2 is looking at the output of the microphone. It's just to the left-hand side of the 100 nanofarad capacitor. Okay, then let's see what it looks like on the ordinary oscilloscope display. Okay, let me turn off spectrogram mode here. Spectrogram is pretty cool, but it does sort of get in the way of our looking at what we really want to see here. Okay, now we're back to looking at the scope as a kind of more normal scope. Let's see. Oh, hey, that's pretty cool. All right, and ooh, that's pretty good. Let's go. Let's see. Okay, so you can kind of see it respond to my talking. So the yellow trace here is channel 1 of the scope. So that's looking at the op-amp output, right, which is over here, pin 6. And then you can see the scale there is about it's a half volt per division. So you can see that when I make a reasonably loud noise, it's about a half volt in amplitude. And so that's 500 millivolts. That's telling you that what's going into the amplifier is only about 5 millivolts in amplitude. And then there's 0 DC offset there. So you can see that this axis, so the yellow trace, it's 500 millivolts per division. I've got 1 millisecond per horizontal division and no DC offset. Now if I go over to look at channel 2, then you can see for channel 2 I have a 5 volt offset, so this is 5, so you can see the blue curve at the microphone is sitting at about 4.75 volts. And then I also have it kind of blown up, well, it's 100 millivolts per division. So you see if I make a pretty loud noise, you'll just barely see it on the blue trace. Oh, let me see if I can blow it up a little more. Let's see, so, whoops. So let's try 20 millivolts per division, but now I need to make it, let me make the offset 4.7 minus 4.7 volts. Okay, that's not too bad, I guess. Oh, yes, you can see the signal before and after the op-amp amplification. Oh, yeah, that's not too bad. I don't know if the doorbell is going to help. Well, okay. So you can see that we're turning a pretty tiny signal into like 100 times bigger signal. And then you can see, well, it was easier to see a moment ago, but you can see that in order for the microphone to work properly, it requires this big DC offset close to 5 volts. But we don't want that to go into the op-amp, so that 100 nanofarad blocking capacitor takes care of that. And then I guess we wanted to ask ourselves also what happens when we tinker with, let's see, well, okay, one thing we wanted to ask ourselves is what happens when we remove that 1 mega ohm resistor. I claim that we will go to either plus or minus 9 volts on the output of the op-amp. So let's see, I've gone to the plus or minus 10 volt scale here on channel 1, and then I'm going to reach in and temporarily remove that 1 mega ohm resistor. And I think on the time scale of like a second or so, I think you're going to see, like a few seconds, I think you're going to see it go to the power supply rail. Let's see how that works out. Okay, so it's oh yeah, so it's drifting. Actually, it takes a while. Okay, it's going to take probably like 10 or 20 seconds. But basically, the bias current from the op-amp is charging up that capacitor. And so eventually, it's going to charge it up enough, right? So once it charges it up to a tenth of a volt, then a tenth of a volt times 100 is 10 volts. And the op-amp output saturates. So, right, because you have to have a DC feedback path. Okay, so we can plug this back in. And, okay, so now we're in business again. And then I think there was one more question that the lab assignment asked. Let me just go read that. Yeah, the one other question that I didn't is what happens if we basically eliminate this 10 microfarad capacitor down here. So if we connect this 100 ohm resistor directly to ground, eliminating this 10 microfarad capacitor. So then what you're going to see is that the gain becomes 101 everywhere. Right now the DC gain is only 1. So if we do that, the DC gain will become 101. And then remember, I bias is about 80 nanoamps. We'll just round it off to 100. So 100 nanoamps times 1 mega ohm will give us 0.1 volts. So then we get effectively, right, we should get like about 0.1 volt here, and you multiply that by 101 and it gives you about 10 volts. So that should be big enough to saturate the output. So I think if we eliminate that, well actually we can either eliminate it or we can just, I can just make a little jumper wire that goes from that end of the capacitor down to ground. And I think, oh, actually it's not as severe as I expected. I'm kind of surprised. So it should be like I bias times a mega ohm, and then that should be multiplied by the gain of the amplifier. So I'm a little confused that the effect is only 2 volts. I would have expected an effect more like 10 volts. Maybe I bias for this particular 741 amplifier is maybe it's only like 20. Yeah, maybe this particular op-amp has only like a 20 nanoamp I bias. Although I think we've measured more like 40 on most of the ones that we've pulled out of the drawers in the past. Anyhow, you do see that there's a significant DC offset. It's not as big as I expected it to be, but it is significant. And the reason is that basically I bias flows into the op-amp through this 1 mega ohm resistor, so then there's an IR offset of, well, I was thinking it'd be a tenth of a volt. Maybe it's instead, maybe I guess it's gonna, it just seems like from observation that it was more like 20 or 30 millivolts instead. And I guess, so it's kind of like a factor of 4 smaller than I expected. Okay, so I think this is a fun circuit because it does something. Okay, it amplifies an audio signal. You can see it. It allows you to actually see, especially if you make the voltage scale something reasonable. Let's make the voltage scale here like that. Then you can actually see your voice. It's even more fun if you put it in spectrogram. You can also put it in FFT mode, I guess. I don't know. I actually think spectrogram mode is really cool. To make that work well, I think you need to go to something like 100 milliseconds per division. And then, yeah, that's pretty good. I guess if we try FFT, here, let's see what FFT looks like. Get rid of spectrogram. FFT. Yeah, that's not as impressive. The spectrogram is really cool. I strongly recommend the spectrogram. It's actually more impressive if you talk at it than if you, but I guess you could, like the doorbell was pretty cool, or if you can sing. I can't really sing. then you could see. Also, compare like ooh, e, ooh, ooh. You could try some consonants. Consonants should give you like or s, pop, pop, pop. Yeah, I think you get this pretty broadband response from like the consonants, like thwap. I don't know. Okay, yeah. So try different vowel sounds and consonant sounds, and I think a vowel sound often sounds like a pretty like continuous note, whereas I think a consonant is usually higher frequency or maybe pretty broadband. But I'm just kind of talking out my ear there. Give it a try. If you find something really interesting, then send us a screen capture of it. Alright, this has gone on for long enough now. I'll see you later.